Welcome to Making Sense of Raster from Bit Depth to Better Workflows. Now, this is our third imagery webinar that we've hosted over the past several months. We're really excited to be discussing this topic today, making sense of raster specifically. And we're joined by three different presenters today presenting this content for us, Kaylin, Crystal, and Pierre. Let's start off with Kaylin, if you want to introduce yourself, Kaylin.
Hi, I'm Kaylin. I'm on the FME Forum Support Specialist team. And Crystal?
Yeah, hi, I'm Crystal. I'm also an FME support specialist here at SAFE.
Yeah, and I'm Pierre. So like the other two, I'm also technical support specialist for FME Forum.
Awesome. And you might also see Dimitri or Dave or Dean in the comments here today. They supported a lot with the webinar content development. So yeah, really appreciate their support with this webinar as well. So feel free during the webinar to get any questions you might have into the questions tab. Between our whole team, we'll be looking at those as we go along here. And we also have the chat, so keep letting us know where you're tuning in from with that chat bar. On the bottom right as well, share your reactions with us with that react emoji button. We love to see how everyone's reacting to the content as we go along. That really fuels us, keeps us going as we're presenting. So yeah, we appreciate people chiming in with the reactions. And then if you do have any audio or video issues during the webinar, that help button on the bottom left will take you through 4 simple steps. The first of which is just a simple page refresh. Okay, so just to go over a bit of a snapshot of what we'll be covering today. As you can see, we do have a very full agenda for the 1 hour today. Crystal's going to be kicking us off with an introduction to today's topic and why it matters, as well as going through some key terminology. Then we'll be going over raster bands and palettes, followed by compression and no data. Following that, we'll be going over formats, properties, and transformers for rasters. And then we do have a section as well on FME and AI, so excited to see that all with you, and then FME for raster processing. Lastly, we'll be going through potential workflow scenarios where you might be applying these learnings from today's webinar and some examples to help inspire you. Following that will be our conclusion, some resources to help you get started, as well as next steps. And then lastly, we should have about 10 minutes remaining for some questions live. So once again, get those in as we go along. All right, so at this point, I will get our presenters to turn off their webcams just to save on some bandwidth for the remainder here. And I'll pass things over to Crystal for our introduction.
Awesome, thank you. Yeah, let's kick off with the introduction. So understanding raster structure helps us to get the most out of our data and makes it much easier to manage and transform them inside of FME. Before we dive deeper into raster concepts, it's important to talk about why understanding rasters matters in the first place. They're not just satellite imagery, they include terrain models, sensor outputs, drone photos, scanned paper maps, and even the pictures we take on our phones. Understanding what rasters are and the underlying concepts enables us to diagnose issues correctly and choose the right tools for our data. That understanding gives you confidence, so you're not just pushing data through transformers, but you're making informed decisions about resolutions, tiling, compression, and more. This allows you to adapt creatively when the data doesn't behave as you expect. Now that we understand why rasters matter, let's dive into some quick history. It helps to take a step back and look at the history of remote sensing, since it explains why raster data looks the way it does today. Remote sensing started in 1858 when the first aerial photograph was taken. The early 20th century was the precursor to multispectral imaging. Then during the World Wars, the airborne photography started becoming organized and systematic. The 60s brought around the first Earth-observing satellites, and by the 80s and 90s, digital sensors became widely used for imagery. Now we have high-resolution satellites and near real-time data streams. Remote sensing explains where our imagery comes from, and raster history explains how we make sense of it. So let's see how rasters have evolved over time. Raster displays emerged in the 50s in the form of pixel-based representations. A decade later, researchers began applying raster concepts to GIS. Soon after, analytical raster GIS takes shape in the 70s. In the 80s, map algebra was formalized, which gave us a mathematical framework for analyzing raster layers. By the 90s and 2000s, desktop GIS brought in remote sensing and raster processing capabilities. From the 2010s to now, cloud computing and AI have ushered in a new era where massive raster datasets can be analyzed at unprecedented scales. All right, we'll just jump into some action now. So for this demo section, we've got a very neat workflow showing how we can use FME to create a tiled web map. Then we'll use that very same web map inside Data Inspector as a background map. So in this demo, we'll specifically be creating a tiled web map using the XYZ scheme. All right, so our workflow begins with reading geotiffs that cover the city of Vancouver. The 36 input geotiffs cover their own extents. Since we want to piece them together into one big raster, we'll use the raster mosaicer, which accepts many raster features and combines them into a single one, which is exactly what we need. Our goal is to create a background map. So with the geotiffs stitched together, we can start adding meaningful symbology to display on top of that imagery. And we'll just give it a second for the raster mosaicer to load. As you can see, it shares one shared extents now. So inside the bookmark are some vector features that we'd also like to display on our background map. For our example, we're using transportation theme data, so we have train stations, train lines, bus routes, and even some park data. Since they're vector data sets, we'll need to use the mapnik rasterizer to turn them into rasters for the background map. We can set the symbolizer, go in to edit the styles, to change any of the color, opacity, width as we see fit for each input. We're using a lot of line symbology, but we can also use other different types of symbolizers as well, such as for place markers, we can insert images into there. We can even use polygons to represent features such as parks. This transformer is also very powerful because we can set the cell spacing and ground extents to be relevant to our data inside the transformer. All right, so now we can take a look at the visual preview to see what we've created so far. And it might take a minute to show up, but when it does show up, we'll see our features with our chosen symbology all rasterized. And we'll just give it a minute to load here. Switch over to the pan tool so it's easier to move around the map. Awesome, there it is. We have our transit lines and train stations, as well as bus routes and parks. And we can just pan around this map to make sure everything has shown up correctly to our chosen extents as well. Nice. So the next part of our workflow is the web map tiler. So here we choose the tiling scheme for our desired web map. For our example, we'll use the Google Maps compatible tiling scheme, which works for the tiled web map XYZ. As well, we set the min and max zoom levels there. Now each zoom level will be written out to its own folder. So I have this test filter here just to show how many features there are in each zoom level. The higher the zoom level, the greater the resolution. So that means more tiles and more features need to be created. We'll write this out using the PNG writer in FME. Clicking into here, we're using a dataset fan out where we'll write folders for each zoom level, folders for each tile column per zoom level. Then we'll finally write the rows as PNGs inside this nested structure. Nice. So this wraps up the workflow steps in FME. We'll now move on to hosting the web map locally. So this is the script that I will use inside command prompt. In the directory that I host holds the tiles that we just wrote out using FME, as well as an HTML file to help visualize the web page. And in the hosted directory, our tile structure is zoom level, column, then rows as PNGs. For this HTML page, we use Leaflet to create the maps over here. That shows the tiled zoom level, column, and rows that we created earlier. And depending on the zoom level, the map will fetch the requested PNGs to display dynamically. Now inside Data Inspector, I pulled up a community map of Vancouver. So let's set the tiled web map XYZ to use as a background map for our data here. We'll add a new background map, specify the source, and set up the URL next to properly fetch the PNGs based on the zoom level, column, and row requested in the XYZ pattern. So closing out of that, we can now use our new background map. Nice, you can see that the background map is now behind our data. This raster workflow is really great for creating custom background maps where the user can decide exactly what they want visualized. So in the end, we successfully created a custom tiled web map to use that also shows the crucial transit information on top of remotely sensed imagery of the city of Vancouver. And that wraps up our demo. So in summary, we used our input geotiffs to create PNGs written out in the XYZ web map tiling scheme, XYZ being respectively the column, the row, and then the zoom level. So an important note is to ensure that you select the appropriate tile scheme in the web map tiler that works with your data destination. And as well, if you noticed, there were .wld world files that were alongside the PNGs in the hosted directory. Those are actually unnecessary for our XYZ background tile maps. FME can do a really great job of performing data transformation with no code, intelligent automation, and offer format interoperability to work with your raster data. We offer very flexible deployment options. The FME platform manifests itself in 3 different products. FME Form, where you can build and author your data integration workflows. You can then publish these workflows to FME Flow for automation. Lastly, you can bring your data to life in FME Realize, our augmented reality tool. We have our roots in GIS and geospatial data. Then over the years, we've responded to our customers' needs, and we now support over 500 data integrations in FME. From geospatial data through location intelligence and IT, our goal is to enable you to use your data where, when, and how it's needed, regardless of its source. Now I'll hand the presentation over to Kaylin for the next section.
Thanks, Crystal. Yeah, so we're going to review some key terminology. So raster, image, imagery. A raster is really just a data structure, and it's a grid of adjacent squares or rectangles. A raster can store anything. So it could be an ortho photo, it could be a calculation like NDVI, scan maps, topo maps, DEMs. And then an image is a subset of rasters that represent things that we can see with our eyes or measure with instruments. And this could include things not seen with our eyes too, so anything outside the visible range. It's anything emitted or reflected. This could be radar, heat, MRIs, like the DICOM image you see on the bottom right-hand side of the slide, RGB photos, multi-spec, hyperspec. And then imagery is a collection of images usually tied to a specific purpose or industry. So if you've ever gone to the hospital for an x-ray, you've probably been sent to the medical imaging wing. So in this case, medical imagery, satellite imagery, ortho imagery. So what is a raster cell? A raster cell is a unit of raster representing some measurement or computed value, where a pixel is a representation of that cell on the screen. We can kind of think of a pixel like a display unit. Usually it's going to be RGB, like the slide you're looking at right now, or grayscale for things like numeric grids. So cell properties include things like size, extents, values, no data values, origin. So for example, the origin of your cell could be the middle, but it also could be any other position inside the cell. And so these things start to matter in certain processes like vectorization. It will affect your output. So a raster band is a two-dimensional array of those cells made up by rows and columns, and it represents either a single measured or derived value. We have an asterisk beside single because it's not always that simple. You can have one value that encodes multiple values. Band properties include things like name, interpretation, which is a combination of data type and bit depth, no data values, number of palettes if there are any. So possible types, that could be integer, so signed or unsigned, and that's really just saying whether your values go negative to positive or just positive. And then we have more familiar things like red, green, blue, alpha, and so forth. Possible bit depths, we see 8, 16, 32. So for context, if you have a RGB24 raster, we can assume that band interpretation is 8-bit, meaning you'd have a red 8, a green 8, and a blue 8 band. A couple of edge cases to keep in mind. So you might come across older or legacy rasters that could be 1-bit. So it's rare, but it still might happen. And then some format specific things. So JPEG actually only supports up to 12-bit instead of 16-bit. And it's important to be aware of these things when you're translating to JPEG so you don't lose any data. No data, it's just a normal value, but in the metadata, we can say it's different and to handle it uniquely. So typically it's something along the ranges of your values, like 0 or 255, or if you've ever worked with elevation data, that 999 number you probably see. So we often hear bands referred to as layers, but this can be kind of misleading. So instead, imagine you have 3 paint buckets, red, green, and blue, and they're all releasing different amounts of paint into one box, where that box is your pixel. So now we're going to review raster bands and palettes. So understanding bands is crucial for format compatibility, such as recognizing that a 4-band PNG cannot be directly written to JPEG without removing a band. And that's under the philosophy that PNG supports alpha bands for transparency. So data ranges and interpretation can influence output size. So knowledge of your value ranges allows for storage savings. So for instance, if the values in your raster don't exceed 255, you really should be writing to an 8-bit container instead of 16-bit. Spectral indices and analysis often use different bands and combinations to quantify various environmental properties, whether that's vegetation health, water retention. And combining bands in this way also highlights the importance of band dimensions, as resolutions and other properties usually have to be aligned in order for them to be combined. So when working with imagery, just remember that some formats and operations have specific band or bit depth requirements. So for example, natural color lands at 8 will use bands 4, 3, 2 in that exact order for natural color. Indices like NDVI will rely on certain bands. So NDVI would be near infrared and red. And mosaicing will behave differently when mixing 3 and 4 band data. So if you're not working with band rasters, you might be working with paletted rasters or raster palettes. So raster palettes are index color tables or color lookup tables, and it's a way of storing colors in a raster image more efficiently by using a list of colors rather than storing the full RGB value for every pixel. We typically see palettes in things like PNG, GIF, or as products like classified data or scan maps. FME has a set of transformers that will help you resolve, manage palettes as needed, so you can remove, add, extract more. So this is an example of a palette. You can see we have our color value on the left-hand side, followed by our RGB value. You'll notice that that has 255 tacked on the end of it, and that's representing our alpha value. The image on the right-hand side is showing that a raster can have more than one palette. So here we're describing the raster with an RGB image, and then we're also qualitatively describing it with a string. So palettes were historically useful because they made files smaller, they were easy for humans to edit, and they allowed for clear class-based coloring. But their use has kind of declined because modern file formats now provide efficient compression, which makes it easy to support full precision RGB data. So really you can store more for less. And this kind of brings us to our next topic, so compression and no data. So compression allows you to reduce file size quite efficiently, and it's quite important in the data age that we're living in. So there's many algorithms for how to compress things. It can either be lossy or lossless, but how does it actually work? So if you have 100 red pixels that are the same color, instead of individually encoding them, compression would encode data line by line or by block. So if you have 100 red pixels, instead of encoding red 100 times, red, 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 you would say from this pixel to this pixel is red. It doesn't really affect the data, it only affects how we store it. So what are the benefits of compression? We can save on file size, performance, storage costs, transfer costs. So if you're sending a lot of data over the internet, let's say you're generating a tile cache, you could be generating gigs worth of data. And so compression would be useful in that case to reduce the amount of data that you're sending over the network. However, how do you know what compression algorithm will best suit your data? Well, we can kind of break it down by what kind of raster do you have. Certain algorithms will work better with certain data types. Next, what kind of precision do you need? So lossy compression will permanently remove redundant data from a file to reduce file size. Here, we might see image quality degrade as less important information is filtered and removed from the image. With lossy compression, once data is removed from the image, it can't be recovered. So that's one thing to be aware of. Lossless compression, though, works a little bit differently. So lossless compression doesn't discard any data, even if pixels appear redundant. Instead, to maintain quality, bit depth is used to store multiple bytes of data on a single pixel. If you're working with large rasters or in cloud-based environments, you might want to consider using a cloud-based format. So COG is really similar to GeoTIFF under the hood, but it's optimized for the cloud. It also supports the read what you need narrative, which has its own storage and serving benefits. So this table is kind of a summary of what we just talked about or reviewed on the last couple of slides. I just thought it might be easier to reference post-webinar. So we're going to jump into a demo now to show you how compression works. So here we're going to read a DEM, but first let's check its size. So the goal here is to compress the DEM. So we can see it's 9 megabytes. And we're going to write to GeoTIFF. So let's go ahead and drag and drop our file. Our reader dialog box pops up. We'll take a look at the parameters. We're going to leave everything as default. We'll click OK to add our source feature type. Now, without caching, we can actually just add a writer. We'll write to GeoTIFF. We'll select our output location. We'll click OK to access the compression parameters. So we're going to be using something called LZW, but ZSTD would be another good one. As you can see, we support a long list of compression algorithms, so we probably have one to suit your data. But we're going to go with LZW, and we'll click OK. And we can run our workspace and see how compression has behaved. So if we look at our output property size, we can see that our file has been reduced significantly. So 2 megabytes. Okay. So lastly, I'm going to review no data. So again, it's just a normal value, but we give it special meaning. So we use no data for areas outside our area of interest or data extents. So where there's nothing or really where it's not important. Moreover, it's a cell that exists in the grid, but it should be ignored for calculations and display. Fun fact, each band can actually have its own no data value. So when doing raster calculations, no data can sometimes destroy the process and sometimes results too. So an ideal scenario would be to remove no data using something like the raster band no data setter or remover, and then to reinstate it back afterwards. No data also can help for reprojecting. So if you're going from something like Lambers to UTM, you might have a slight rotation in your image, and you might have a black border. No data can help remove those borders. Last thing I want to mention here is no data is also or can be used for visualization, but no data differs from alpha. So alpha transparency can be a range or hold some form of semi-transparency where no data will either be visible or visible. And we'll show you how to remove black borders from an image now in FME. So you can see here we have our stack asset reader, and we have used the reader parameters to dig into our stack collection. We're selecting our item, which is holding our actual data. We'll click run, and we'll take a look at our RGB photo. So this is a RGB image of Houston, Texas. And you can see that we have these black artifacts around the edges. And so by clicking around, we can see that all bands have the values of 0. And so we can set the value of 0 in our raster band no data setter. So by applying our no data value, we can see that those black borders have actually been removed.
Yeah, so in this section now, we'll go over the components of raster formats, key properties that define how rasters behave, and the transformers inside FME that let us manipulate them. So we can think about the format of a raster as a container. The container or format defines how different components are stored. So formats encode cell values differently, handle metadata and georeferencing differently. As well, they organize bands, compression, and tiling in their own ways. The format defines what combination of these components can exist, and where FME shines is being able to translate between them even when the formats don't align. Raster properties are like the building blocks of a raster. These fundamental properties include the number of bands it has and what data type is used in those bands. Palettes and no data values also influence how the raster is displayed and processed. Another key property is resolution, the number of rows and columns. Some formats can have multiple resolutions, while others may have dimension limits. How the raster is compressed, whether or not it supports georeferencing, and what kind of metadata it has are all differentiating properties of a raster. An increasingly relevant property is cloud readiness, which is how rasters can be efficiently stored, accessed, and analyzed within a cloud computing environment. Now that we know what makes up a raster, the next step is understanding the tools we have in FME to transform and analyze them. FME provides a wide set of transformers for every aspect of raster handling. We have transformers for manipulating bands, working with palettes, and extracting raster properties. There are pixel-level analysis tools like the Raster Expression Evaluator and Raster Cell Value Calculator, as well as structural tools like the Raster Mosaicer, Tiler, and Pyramider. Some transformers bridge rasters with vectors or 3D data, others integrate point clouds or attributes, as well. More recently, we've added connectors for AI and web services that let you incorporate vision models or external APIs. Altogether, these transformers give you a flexible toolkit for building almost any raster workflow you need. One transformer deserves special attention because it's incredibly powerful and widely used, the Raster Expression Evaluator. Essentially, it is a calculator that works at the pixel level, targeting the cells that you decide with your expression. Some of the capabilities it has includes performing masking, pan sharpening, and brightness correction operations. We can use it to perform simple value assignments, assign values from attributes, and evaluate expressions on pixel values. And of course, you can use conditional logic from basic to deeply nested expressions to create precise pixel level rules. This gives you full control over the raster right down to the individual cells. Here are two examples of raster expressions. So for the first expression here, if band 0 in raster A has less than a value of 255, then change the current value of the cell to 200, or else leave the value at 255. For the second expression, if bands 0, 1, and 2 are greater than or equal to 230 in raster A, then set the current cell to 0, or else leave the value as 1. And also, Pierre is going to be using the second expression in his demo to create a raster mask today. Jumping into the next section, we've covered how rasters work and how to manipulate them in FME. So let's now just explore how AI can elevate these workflows even further. AI can enhance raster workflows in several powerful ways. It can assist during development by recommending libraries, writing snippets of code, or helping with debugging. It can also guide raster analysis by writing expressions for tools like the raster expression evaluator or creating filters for the raster convolver. And beyond analysis, AI models can actually generate or modify imagery, creating textures, retouching satellite scenes, detecting objects, writing OCR, or even producing fun artistic outputs. These capabilities expand what's possible in FME, especially when paired with web APIs and image models. To connect AI with rasters, we often need a way to move images and data between systems. This brings us to raster encoding and blobs. Unstructured data like images, audio, and video are often encoded into binary large objects or blobs. A blob is just a chunk of binary data, often base64 encoded when transmitted through APIs or AI models. LLMs, APIs, and XML databases all rely on blobs to store or move attachments because they package binary content into text-safe format. This is exactly how AI returns edited or generated imagery, and FME can decode these blobs back into rasters for further processing.
So now we're going to show you how imagery is kind of transferred between AI services in FME. So here we're going to use our Google Gemini stylized portrait maker. We're going to show you our input image. So we have Dimitri here as a JPEG. To actually send our data to the AI service, we'll take a look in the custom transformer, but this is our output. So you can see that we've turned him into a traveler, a desert traveler. So how does this actually work? So in our Google Gemini styles maker, we are going to extract our raster into a blob. So here we'll select our format, in this case JPEG, and that's going to encode the data. We're going to use that in our upload body in the HTTP caller. And then we're going to get that raster back and actually use a raster replacer to reinstate that raster geometry. And so you'll see we have that same output image we just saw.
Okay, so now I'm going to talk about how about using FME for raster processing. So some of the scenarios where FME is well suited and some limitations as well. So first, where FME fits. So essentially, if it's about the data and where it goes, we can use FME. I'm quickly going to go over some of these functions. So tiling, clipping, and mosaicing, like we saw earlier in the Flash demo. There's also format conversion, which is one of FME's biggest strengths because it supports reading and writing from many different raster formats. And then on the image on the right, as you can see, there's overlaying, draping, and texturing geospatial data. Well, where basically a vector layer was overlaid on some orthophoto data, and the whole combined image was draped over a DM to give texture to the final surface. We'll see more of these functions in action in the upcoming demo. And next, some limitations of FME. It can broadly be broken down into two categories. The first is image editing and visualization. So this includes manual style editing, some selective adjustments, real-time interactive visualization, layer-based editing. And the second category is specialized analytical workflows. So this would be something like advanced remote sensing analytics that would require atmospheric correction or machine learning based image analysis. In this case, you would use third-party tools via an API or command line call, and terrain modeling beyond standard hillshade or slope. FME handles hillshade or slope, but for anything more advanced than that, like network modeling or flow accumulation, other tools are better suited to the task. Important thing to note here is though FME itself doesn't perform these advanced analytical functions, it does allow you to integrate these tools into your workflows via something like an API caller or a Python caller. Next, we're going to put everything we learned so far together in a potential workflow scenario. For this scenario, we have received some raw orthophoto data that needs to be converted into web map tiles for a transit map of the city of Vancouver. We'll go through processing the raw data into the clean dataset that Crystal used in the Flash demo earlier. These rasters contain irregular white areas that we want to get rid of that also have non-uniform pixel values. This is likely because at some point there was some JPEG compression applied to the source data. To prevent artifacts in the final web map, we want to standardize these white areas and add transparency. Cleaning this up will be a bit of a challenge as we have to determine the range of values that make up these areas and then get rid of them. Then we will want to add an alpha band and write to a format that supports transparency, in this case PNG, to create the web map tiles. So now I'll go into the demo where we go over a sample workflow that handles this data cleanup.
So how would you do something like this in FME? First, let's take a look at what we have. I have the source data open here in Data Inspector. The white areas are what we want to get rid of. But to know how to do that, we also want to look at the areas with valid data. If you zoom in very closely, you can see here that each individual pixel has 3 band values, red, green, and blue. And the different values mean how much of each is shown in each pixel. Let's go over to the areas now with no data. These are the white parts that we want to get rid of. Some of them are full white, meaning 255 for all bands, and some aren't, which means we can't just isolate one value and get rid of everything that has 255 for all bands. One thing to note, though, is that all the white areas have RGB values that are very close together. All right, now onto Workbench. I have here the completed workspace, and I'm going to step through the different portions to show everyone what's going on in each part of it. First, we will get rid of the images in the dataset that have no valid data in them. Since they are all close to white, the range of possible value in each image is quite small. One of the fastest ways to do this is to use the raster statistics calculator. This transformer calculates various statistical measures for bands in the raster. In this one, we will use band 0, which is red, and ask it to find the minimum. Images with real data will have a wide range of values, so we expect the minimum value to be at or close to 0, whereas tiles that are all white will have a value that's much closer to 255. If we inspect the data after it's gone through the transformer, there are some images that have a minimum value of 245, meaning that all pixels are close to or fully white. Next, we will use a tester to test for the images with minimum values of 245. Those that do are now taken out of our processing workflow. This did not, however, get rid of all the no data portions that are on images that do have valid data in them. And we want to isolate these areas, and one of the ways is to create a vector clipping mask, which we'll then use to cut out the white areas from the source data. To create this vector clipping mask, we first want to capture all the remaining white areas in the image. To do so, we'll generate a raster expression within the raster expression evaluator to find the extents of the areas where there are no data. In the transformer, we set the mode to 1 raster, referred to as raster A, and change the interpretation to an 8-bit unsigned integer band. Now, we'll go to the expression itself, which the transformer uses to calculate and reassign the values. We start with if, and then A0, meaning band 0 in the source raster, corresponding to red, is greater than or equals to 230, and A1, band 1, the green band, is greater than or equals to 230, and finally, A2, band 2, meaning blue, is greater than equals to 230, comma, 0, meaning then set the value to 0, comma, 1, meaning else set the value to 1. As all of the white areas in the images have very similar RGB values, and all of them are quite high, this expression will set values of all those areas to 0. Now let's look at the cache data. The fully black areas correspond with the white areas in the source data. There are also many dotted areas that are black in the portions that are supposed to have valid data, and we'll get rid of those later. But the reason they are there is that there's only so many colors that a raster can represent. And if we think about some rooftops, boats, or vehicles that might be colored white or really light gray, you can imagine some similarities in pixel values. Now, since we're only creating a clipping mask, we can get rid of them when doing the vector processing, but I just wanted to highlight it. Back to the output of the raster expression evaluator, there are only two values left, 0 and 1. Next, we'll use the raster band no data setter, setting a value of no data to 0 for the areas that we filtered using the raster expression evaluator. Looking at the result shows the outline of the new clipping mask, basically the areas where there are valid data. We'll use the extents of this to create a polygon clipping mask to clip the initial data set and generate our final area for the web map tiles. I will only go over the next portion briefly because it isn't the focus of this demo. We are essentially creating a polygon feature and cleaning it up by dissolving and using donut hole removers to get rid of the no data portions inside the polygon that we want to use to clip our data. I do want to draw your attention to the raster extents coercer, which creates a polygon based on the extents of the data present in the raster. So now let's take a look at the final clipping mask. We can take the source data and connect it to the clipper transformer as the candidate, and take the clipping mask and connect it to the clipper port of the clipper transformer. Inspecting the clipped output shows the data no longer has any white areas that have no data in it. We do have an issue though, because if we want to mosaic our data into a larger raster, the final output will be rectangular, and there will be areas with no data in the final image. To deal with this, we want to add transparency via an alpha band. This alpha band will allow us to render the portions with no data in them fully transparent. To do this, we add the raster interpretation coercer and set the destination interpretation type to RGBA 32. This means red, green, blue, alpha 32, 8 bits for each band. All the resulting pixels will have an alpha band, and an alpha value of 255 means that it's opaque. This is now ready to go into the mosaicer, as from here, no data areas will have an alpha value of 0, meaning that they will not show up in the final output. From here, it is extremely similar to the Flash demo. We import our various vector layers that are in Map Info tab, GeoJSON, and shapefile formats, which is one of FME's strengths as it supports many different formats, style them in the MapNIC rasterizer, and finally feed it into the WebMap tiler to create WebMap compatible tiles. Once all the tiles are completed, there is one more step that I want to showcase, and this is more for space optimization. If you remember, the tiling process creates many tiles at different sizes. Especially in the closer zoom levels, there is a high chance that there are some tiles that will have no data, in this case meaning having an alpha value of 0 or fully transparent. To save space, we don't want to write these out, so we'll use a similar procedure to earlier in the demo to find out where there isn't any data. This time, instead of using a red band, we are going to be using the alpha band. So I've added a raster statistics calculator here to find the maximum value of band 3, which is the alpha band. Inspecting the results shows us that there are some tiles that have a maximum alpha value of 0, meaning that they are fully transparent, and we're going to use a tester to sort them out of the data stream to ensure that we don't write them, and then feed the tiles that do have data into the test filter and finally into the writer. The final output is essentially identical to the one from the Flash demo earlier, but slightly more space efficient as we have 1,766 fewer tiles being written out and read into the web page.
So to summarize, we used the raster principles from this webinar to clean up a raster dataset, integrate with vector data, and optimize space in the creation of web map tiles. And we also learned that FME has a wide variety of tools that can be used to solve raster-related problems, all while allowing you to integrate other formats into the same workflow. Something I'd like to note is that you can solve the same problem many different ways in FME. You could also have used the raster cell value replacer instead of the raster expression evaluator to get rid of the white areas in the image. Now, I'm just going to start off the conclusion. So basically, what did we learn in this webinar? So after a history of raster data, we learned the basics of rasters as a data format. We defined and reviewed key raster terminology. And lastly, we showcased how FME can create and improve raster processing workflows. And now I'll pass it off to Elizabeth, who will finish off this portion of the webinar.
Fantastic. Okay, I'll wrap this up quickly. I know hopefully we'll have a few minutes for a couple questions live here. And just a reminder to get your questions in before we get to the live Q&A. But in the meantime, if you are newer to Safe Software, just so you know, we have been in the data integration game for over 30 years now, with over 200,000 worldwide users and 140 plus global partners. FME is an all data NEAI platform. It is the only all data NEAI platform. And we connect to it all data, velocities, locations, types, and any AI technology. We do have some resources to help you get started after today's webinar. We've got 4 that are linked on this slide here. And so we encourage you to download the deck. You can click the apps button on the bottom right, handouts, and then download. That way you can scroll through all 4 of these different resource links. If you're newer to SAFE, you might not be familiar with our free resources. We're all about them. Our academy is home to free instructor-led training. And we also have hundreds of on-demand webinars available. So safe.com/webinars, check those out. If you're a member of our community, you can claim your community badge as a thank you for joining us. I'll drop that code in the chat. And if you aren't yet a member, you should take a look. It's a great place to network with other users alike. You can also get any feedback or advice. It's a great place, great forum to post any questions you might have. And with that, we do have about 10 minutes here remaining for some questions. We got some great ones that came in. So I'll invite the team if they want to join me on the stage here and we can take a look through. Thanks everyone for dropping questions, and it's great to see the comments and the reactions as we went along here. All right, I think we're all here now. So was there a question we wanted to get started with, team? Did anyone have one in mind?
I have a couple, but if anybody has something quick they want to do first.
Go for it.
Okay, so I did see there's 2 that sort of popped out. One was how do you deal with black backgrounds when a simple no data value replacer won't do the trick? I did want to emphasize the value of the raster cell value replacer before you do things like no data. It also can be very helpful for classifying. I know that I think one of the demos that might have used you can do something similar with the raster expression evaluator, but the cell value replacer is really easy because you just give a cell range. So let's say you're trying to set something to black, but you've got some little bits of dark gray. So you could basically say all the values, above 250 or below, let's say below 5, let's say for dark values, set everything 10 and below to 0. So you can do that pre-filtering or classifying of, and then push the very dark grays to black before you set your no data value to 0. So that was just a quick one there. And the other one was a little bit more complex, but I found it entertaining because it shows the power of FME. So there was a really good question by Katrine. And then she says, I have a point data with the number of households. I would like to convert it to 100-meter raster, calculating the sum of all households that are in a raster pixel. So in that 100-meter cell size. Then that should be the value of the results. So you can actually do this in FME. There's probably more than one way, but one way that came to mind is you can use a tiler transformer to make 100-meter tiles. Then you can clip your points by those tiles, and then use for everything that goes per tile, you can use a point cloud combiner to make those into point clouds, and use the point cloud statistics calculator to sum up the number of points per cell. And then once you have that, you can use that as the value for your numeric rasterizer when you convert. So you can essentially do a geometry replacer of all of those, that point cloud with a single point that has the sum of households or any other value you want to use, and then use that in your numeric rasterizer. So if that sounds a little complicated, I'm happy to follow up offline. So there's just a couple of ideas there, but just to say, just as a point, that FME is very powerful for converting or casting between different representations of data. And one that sometimes people forget about is that a point cloud is an array, and so is a raster. And FME is highly efficient casting between those, because we don't have to convert from point cloud to individual features and then back to raster. You can go direct. Cool. Any other questions that came up or anything in the chat? Just having another look.
Yeah, it looks like we've gotten to most.
Bruce Harold has something. Are there AI tools that we can use a raster prompt and return processing suggestions? Yeah. So does anybody have, from the group here, does anybody have experience? I'm assuming there are ways of funneling in raster data as part of your prompt.
Yeah, I know we can
funnel
send
data
them,
to an agent.
send them to and from, but I don't know if we can, get suggestions back.
Yeah,
I mean, obviously, there's lots of ways in FME to integrate with AI for doing things potentially like feature extraction. So different AI or ML methods, and using either AI agents or third-party libraries. But I haven't personally played around with that. I'm not sure. Maybe Dimitri has. Has anybody else on the crew here tried that out? It's a good question. Any other unresolved questions?
And just to note as well, I know Bruce has already had to hop off for something, so maybe we can also send him a follow-up note on that.
Yeah, we'll follow up that offline.
Perfect. Okay.
Daniel was just asking. Oh yeah, that's been answered. Okay.
Yeah,
Anything
I'm going to
that
give
wasn't answered, or?
I'll give everyone a moment or two longer. We still have a few minutes here to answer a question or two more. But while the team's just reviewing, in case there's another one we can pull up, I figured it might be worthwhile to share in case you have yet to hear about it and you've attended. I mean, if you attended even just today's webinar, we do have a contest going on right now on our LinkedIn page where you can share your favorite webinar moments from the year. Your favorite moment can even just be a simple sentence for the chance to win a $25 gift card. So just wanted to shout that out in case anyone's interested in joining that contest. But yeah, maybe back to Dean.
I did have one more that came up. So Lily had a question about when you're doing raster to vector conversion, sort of going the other way. How can you minimize the number of polygons generated? And that's a very good question. So I'm kind of a big fan, as you might guess, of the power of FME to convert between these different representations. But that's a very common problem. If you just take any old raster and throw it through a raster cell coarser or raster to polygon coarser, you're going to get a gazillion polygons, and it's not going to scale very well. So that's why I would circle back to one of my favorite transformers is the raster cell value replacer. So you have to pre-classify. So if you've got floating point, obviously you're going to get tons. So then you could convert to int. But even that, you're probably better off. Let's say you had elevation data with floating point for elevation values. You're going to get millions of polygons. If you classify that into 50 meter, let's say 5-10 meter bands, then you could use a cell value replacer, which now actually we've improved it so you can do multiple classifications in one definition, and you could classify that into let's say 25 meter bands, and so then you're only going to get a polygon for the data that's in that band of values, so, or in that range. So pre-classifying before coursing is really key.
Awesome. I think we've gotten to all questions now, unless the team sees another. New one.
And
just
is there a resources slide just to pop up? I'm just curious what we had there for resources.
Yeah, we did have one. Yeah, I can bring that up here again. And I do see a new question from Chelsea. I'm not sure if that's one we can address before. I know we're at the top of the hour. Maybe we have time just for a quick one here.
Arc hydro type analysis. So, I think we have, yeah, I mean, there is some path type, like sort of stream network type stuff, but it's not going to be anything like Arc hydro in terms of watershed analysis, but yeah, stream priority calculator, network cost calculator, shortest path finder, stuff like that. But and there's topology transformers if you're looking at stream at networks. But when it comes to actual hydrology and drainage and I think watershed calculations, that I don't think we have anything along those lines. Although there's probably ways of doing that, some of that analytics yourself.
Awesome. Okay, I recognize we are just past the top of the hour. Thank you, everyone, for joining us today. We really appreciate your time. Huge thank you to Kaylin, Crystal, and Pierre for preparing and presenting today's content, as well as Dimitri, Dave, and Dean on our team for advising on content as we prepared this webinar. And huge thank you to our whole audience for joining us today. We hope you got a lot of value out of today's webinar. If you do have a moment to fill out our survey, we really appreciate any feedback. Thank you, everyone, and hope you have a great rest of your day. Bye for now. I will leave things running a couple minutes longer. So if you do have a question that you think of, we'll stay online for a couple more minutes here. But yeah, have a great day.
Thanks, everybody.
Bye for now.